So I have, in talking so much about continuous valued MRFs, I've been inverting a little, at least the prepondering that we've seen, or the preponderance that we've seen in the last decade or two of discrete valued MRFs. So discrete valued Markov random fields. Sorry, have been much more standard than continuous valued MRFs. And now to recover a little after the perhaps many formula, I want to start by revisiting or visiting a few applications. So the first one is, again, from, let me mention once more, the Boykov and Jolly model from last week. So we have a simple Cartesian grid, 4 connected, and we have a range of the random variables that is either 0 or 1. This is why we talk about a discrete valued. And then we have unary terms that bias towards foreground or background for each pixel. And we have pairwise terms that encourage adjacent pixels to have the same smoothness, but less so if there is a strong image gradient. So this was an example of a conditional random field. I want to give you another example of a conditional random field, or of a application that is often addressed using conditional random fields, namely semantic labeling. And oops, it disappeared. And semantic labeling means we want to assign each pixel in the image to a class, where classes can be such things as apples, pears, bears, whatever you have in your natural habitat. And the way this works typically is to have unary terms that, for example, provide an SVM output that has perhaps been shoved through a sigmoid. So for example, a support vector machine prediction based on a bag of words representation. And we will, in a few weeks, hear in more detail what this is, bag of words representation. Or you could take local color features. So let's say if it's green or red, then it's more likely to be an apple than a bear. The superpixel that you're looking at, and so on. The pairwise terms, you could also have things higher than pairwise, but it's quite typical to use only pairwise terms. For example, the Potts potential, meaning if you have the same label in adjacent pixels or superpixels, you pay no penalty, and if you have a different label, then you pay a penalty of 1. And I'm always talking about pixels or superpixels, so you can, for example, partition your image according to the the gradients that you find, or any There's a large number of methods to generate superpixels. We've talked about one of these, the watershed, but there are many others, and we will talk about others also. So you can partition your image and then associate one random variable with each of the superpixels, and then include, for example, pairwise terms for each spatial neighbor. So if these here share a face, then I would connect them by a binary factor, and I would connect these two, and I would connect these two, and so on. So by any two pixels or superpixels that are adjacent can be connected by such a pairwise term. And I have a screenshot here from a website called sceneunderstanding.com. And I like it because it has trained such a pairwise conditional random field, as I've just described in brief, on the so-called MSRC21 dataset. It's a dataset of a few hundred images in which all contents have been classified into 21 classes, which include bicycle, flower, sign, bird, cook, and so on. And also a black class, which means none of these, I guess. And this website has been trained on this data set, and it allows you to upload any image that you like, and it will make a prediction on it. And I've browsed this a little bit. Perhaps we can also do this here. I've browsed this website a little bit and taken this image pretty much at random. And so let's say this one here. Here's the original image. And oh, that one's actually not bad. Look, the face has been found. Hair, I admit, would be, okay, hair is not a class of its own, but it would also be difficult, yeah, with this pink. Then the thing in the back, I'm not sure, you know, this purple color, does that mean airplane or does it mean boat or book? Or oh, maybe it's building. That would be actually be correct, yeah? Or we could say it's correct. So, you know, it gives you an impression of the level of accuracy that is attainable, which is, you know, so-so, it's okay, which is not the fault of the authors, of course, but the fault of the model. And you can upload your own image and see how well computer science does on your image. However, be aware, I think your image is then going to stay on this website. Yeah? And this is by the authors of the Darwin code, in particular Stephen Gould, who is now working in Australia. So here's another example for a discrete Markov random field, where discrete means we take one out of these 21 classes. And by the way, these unary terms, let me say another word about them. They are, so the Ising model that I talked about first, the Boykov and Johnley model, that was a binary Markov random field. And the one of the kind that you've seen here with 21 classes, I could call it a multinomial Markov random field. And if I wanted to be more precise here, then in this particular case, it would be a multinomial pairwise Markov random field, because it only depends on, so the highest factors that I have are of order 2. And if I want to be even more precise, I could call it a multinomial pairwise conditional random field, because the potentials here typically are made to depend on the image content. So yes, we penalize label changes, but we will penalize them more so if, for example, the two adjacent superpixels are very similar in color or so. So now I wanted to say a word about this multinomial, just as a side remark, really. A multinomial is a discrete probability model where you have to specify two sets of parameters, namely a vector pi and then a number n of experiments. If you want to create realizations, and you could say that you sample from this into a random variable x. And for example, my vector pi, if I have three classes, could be, let's say, 0.1, 0.05, 0.85. Those are the probabilities to sample one of the three classes, and n is then the number of experiments. And this is a recipe to allow you to compute the probability, for example, of obtaining a sample. Let's say if I take n to be 5, then I could obtain a sample 0.05, which would have quite a high probability, or I could obtain a sample, let's say 1.04, which would also have a pretty high probability, or I could obtain a sample 0.50, which would have a very low probability. And so the multinomial gives you, the closed formula on how to compute these probabilities. And this model here, it's called multinomial, but really we don't do n experiments in each pixel or superpixel, but we just do a single experiment there. And such a multinomial with a vector pi of probabilities for different classes, and with just a single experiment being performed, is also called the categorical distribution, or the multi-nulli distribution. And I'm mentioning this, so this is just a special case of the multinomial with a single experiment being performed. And I'm mentioning this because categorical has been invented very recently by a few Wikipedia editors, and it's very interesting if you read the edit, or the talk page of Wikipedia, then you have these people arguing that if it's a good name or not, and secondly arguing if it's been used anywhere in the literature. and in fact it seems there is no printed evidence of it anywhere, but I think since the Wikipedia article exists, it starts to catch on. And second term, the multi-nulli, which is an analogy to the Bernoulli. So far I've seen used only in Kevin Murphy's nice machine learning book, and this was proposed by then master student Gustavo Lacerda, and Kevin Murphy liked the term and has been putting it in his book. Okay, so we see vocabulary generation in the making here. And don't get me wrong, I'm not criticizing it. I'm just, these are useful terms, I think, to refer to the special case, and I just wanted to say that they've not been around for long. Okay, I want to give you another example for a discrete Markov random field. This is a piece of work by William Brendel and Sinisa Todorovic from NIPS 2010. And very similar work was published by these authors in ICCV 2011. And by the way, this line of work here later ended up in winning a couple of VOC challenges in I think 2011 and 2012. So in VOC is or the Pascal challenge, it's an important challenge in high-level computer vision, where the task is to detect objects or to detect and segment objects and so on. So here the task is, in this NIPS paper, the task is to find a good segmentation of the image. And the authors proceed as follows. They find a generous set of oversegmentations. So for example, You could use a watershed algorithm where the watershed is built on different filter responses, or you could use slick supervoxels with a varying size of the superpixels, or you could really use any low-level segmentation algorithm that you like, and then they all have some kind of parameter, and you can vary this parameter, and you will get a number of segmentations, some of which are shown here. So you see that on the right-hand side, for example, you've partitioned the image. I think this is the dome in Florence. You've partitioned it here into very few superpixels, and on the left side here, you've partitioned it into very many superpixels. So here, for example, it is apparently some kind of scale parameter that was varied in producing these oversegmentations. Now we can take all the superpixels from all of these oversegmentations and put them in a single graph, which is what has happened here in figure B. So let's say this guy could come from this superpixel, and that guy, I'm making this up of course, could be from that superpixel. So in particular, if we have a total of let's say n superpixels taken together, so jointly from all of these oversegmentations, then you would here construct a graph with n vertices in figure B. Now these two superpixels that I've just shown here, and let me show another one and pretend that this superpixel here, let's say this superpixel here belongs to sky in that image. They have one interesting property, namely they can overlap or not. So if you take these first two examples, this example here and this example there, they overlap, and hence there is an edge created in this so-called conflict graph. Whereas, okay, this doesn't work. I need this is wrong. I would need here to identify a pixel which overlaps with the one but not with the other. Okay, if you permit my cheating here a little, I'll revert my argument and say this one was this superpixel and that one was that superpixel. And then I could take one, for example, this one here, and declare it's this third one. You see that it overlaps with the one but not with the other. Okay, so in summary, the conflict graph has an edge between any two superpixels that overlap spatially. Now each of these superpixels will also have some kind of quality. So I can associate with each superpixel a unary term that says how well does it explain the image. So for example, a very tiny superpixel, you see on the left-hand side here some very tiny superpixel, does not explain much of the image, and hence I would give such a superpixel a low reward. Also, if there is a superpixel that, let's say, somewhere in its middle has a high image gradient, or a superpixel that combines pixels of very different color, would also be one that doesn't look very helpful. So this would also get a low reward. On the other hand, a large superpixel that somehow, let's say, has image statistics that match those in a ground truth over segmentation or ground truth segmentation, that would be a good one. So I could train this in a supervised fashion. If you provided me with a training set of segmented images and told me that these are the correct segmentations, then I could train, I could also compute, these auxiliary over-segmentation on those images and train a unary term that tells me, is this particular superpixel a good one or a bad one? Is it part of the ground truth or not? Anyway, you get the idea. I have unary terms. And to get a segmentation as shown in C now, I would like to pick superpixels of high merit. So superpixels that give me a great reward and that do not conflict with any of the others that I have selected. So in this particular case here, the unaries are not shown in the sketch B, but in this particular case, the optimum solution, let's say, involves switching here the green superpixels on because they give you high merit, and at the same time, they do not conflict with each other because there is no edge between any of these activated superpixels. And that too is an example of a Markov random field, but one, I was getting a little bored of these pixel grids. This certainly does not live on a pixel grid. This is a Markov random field which lives in this, funny space of the set of all superpixels that you found. So actually, in this plot here in B, the space has no meaning at all. It's just a graphical representation. Really, the representation that we have is in terms of this graph, but where the vertices were placed in this sketch here is arbitrary. The paper is called Segmentation as Maximum Weight Independent Set, because this is the problem that you solve. So maximum weight independent set means you look for a set of non-conflicting vertices that give you the greatest reward. So we want to maximize, I don't want to write energy now, let me say a score S of X, which is given by a reward theta I associated with superpixel number I, and X here is now an indicator variable which says the superpixel is on or off, minus, I'm now putting this into the objective function, this rule that conflicting superpixels must not be activated. So let's say I'm summing over I and J, where J must be connected to I by an edge in my graph. And I'm writing this here as a potential function, xi and xj. And I'm maximizing only over binary variables here. And this potential function, can you tell me what it should look like? So xi can be 0 or 1, and xj can be 0 or 1. So my x are now indicator variables, meaning I select the superpixel to explain or to obtain an overall segmentation. And psi is now the penalty term that says, you see there's a minus here, it's a penalty term which says that adjacent in this graph vertices must not be activated at the same time. No. Yeah, or explain. Yeah, but if both are off, yeah. And where? Where's the 1, 1? No. So if one is switched off and the other is switched off, I have no conflict. So I put a penalty of 0. Can you go on? Yeah. Oh, okay. I'm sorry. I misunderstood you. Okay. So if one is switched on or the other is switched on, it costs nothing. If both are switched off, it costs nothing. And if both are on, it's infinitely expensive. So this is the, if I want to express it as a truth table, this would be and here. Okay, and this would be the penalty. Okay, and then this parameter here tells me how well does superpixel I do in explaining the image. And now depending on how I train this, I can use this to devise an unsupervised segmentation algorithm, or I could also train this, and that's what these authors here have done. I could also train it to predict one of the classes, one of the semantic classes, cow, cow, dog, cat, etc. Okay, so this is also a Markov random field. Maybe something that, yeah, it's a binary Markov random field. So another example of a discrete Markov random field. And by the way, down here are a couple of results from this NIPS paper. On the top is an image. Then in the second row, some other method, 7, whatever reference 7 is, except the rightmost column, which is here. This is reference 25. And this is the NIPS paper that I was just talking about in this last row, showing you the kind of segmentations. And for example, if you compare here, then these small blobs have gone away, and also a somewhat different shape was selected here. If you compare to this method 7, and now you can argue which one you like better. But it's a good segmentation method. Okay, so this much for motivation. Why should we care about discrete MRFs? And then I wanted to give you a couple of examples that accomplish different things.